This is a lecture on expected value for discrete probability distributions. I'll also cover the topics of expected value in bonds and insurance. This is not covered in Mendenhall, but these are interesting problems and they are on the homework. For this discrete probability distribution, we're only going to look at finding the mean, which is also called the expected value. It can be written with the symbol for mean from probability. Often it's written EV for expected value instead of E of Y. Mendenhall does this. I generally use EV. And to get it, use sum. This will look familiar. You're summing over all the Y values that you have. You take Y times the probability of Y. It helps to have everything in a table. It makes it easier to do the calculation. So here's an example in which we have a die that's been loaded. Again, they usually aren't loaded, they're filed off on one side. I don't know if that's useful information for you. Okay, so here's the value of Y. This is a die. It can turn up with 6 sides, 1, 2, 3, 4, 5, 6. I'll use it. All right. And I know the probability distribution here. The probability that 1 will show up is 1/6, 6 will show up as 1/6, but here these are a little lower because these are a little higher. All right, so note that this has to satisfy the probability requirements. All the P's, all the probabilities have to lie between 0 and 1, and they have to sum to 1, and they do. So if you add up all these probabilities, just add them all up here, you get 1, which is as it should. Okay, for the expected value, let me write that equation again. So the expected value is going to be the sum, and in this case I'm going from Y equals 1 to 6. Those are my 6 values here. Y times the probability of Y, each Y. So the first Y is 1. It has a probability of 1/6. Let me clear this for a second. So you have a 1, the probability of 1/6. You multiply those two together. Okay. Then you go 2 times 1/12, and you multiply those and add. And you go through the whole list, 6 times 1/6, and that will be your last term here. You're adding up all these probabilities. This is your expected value, 3.2517. Okay, you'll never, of course, roll a 3.2517, but that is the expected value. It's more useful in other calculations. So here's an example for the lotto. We'll look at the Powerball in New Mexico. The prizes that will be obtained here, or that may be obtained, $10,000, and there's one of those. $100 prize, 34 people get that, or 34 ticket holders. $7 goes to 977 people, 4 to 2,125 people, $3 to a little over 4,000 people. The rest of the people just paid the $1 for the ticket. The total number of tickets sold is 195 and some million, and they cost $1 each. Okay, so here's the scenario. From this we can calculate the probabilities of winning the 10,100, 4, 5, 3, or simply losing the dollar. Now remember that you don't get your dollar back when you win the 10,000, so all you're going to get back, actually win, well, they give you 10,000, but you had to pay the $1 in, so you're really winning $9,999. Okay, so here's the value. This is what you're going to get back. Remember, do the calculation completely. You don't win 10,000, you win 99,999 because the $1 left your pocket. All right, 99,632, and then you have a -1 here because you paid your $1 and got nothing for it. Now I put the chance of winning here. There's one of those prizes divided by the total number sold. I did that all the way down this list. If I add all these up, they come to 1, which is what they should do. The expected value, for the expected value, I'm going to take this, I can never draw on this value, and I'll multiply it times its probability. Then I'll take the 99 and multiply it times its probability and add those together and just go down the list. Because they all have the same denominator, I just put the denominator down here by itself. So that's why the calculation looks like that. When you get through with all this calculation, you find that the expected value is minus $1. Now, I've heard it quoted that the expected value for the lotto is 50 cents. That is so untrue. The expected value is usually minus whatever you paid for that ticket. Okay, here's the calculation right here. Now we're going to do a very elementary calculation for bonds. As you know, the financial calculations for bonds, that's very complicated. We're not doing anything that complicated. We're just doing some bare bones expected values. So we have to look at the amount that the investment can return if things go well, the amount you're going to lose, which is usually everything you paid in, if things don't go well. We're going to create a table of these numbers. We need the probability that things will go well, will not go well, and the probability things will be okay. So here are some numbers. Say we put $10,000 into some bonds. They have a 4% return. Okay, if things go well, what am I going to get back? $400. I won't lose the $10,000 and I'll get an extra $4,000. All right. There's a 2% default rate. Actually, I want to make a comment here because it looks like there's a period in front of the 2, but there isn't. If there's a 2% default rate, then the chance that it's going to default in decimal is 0.02. What if the default rate was 0.2%? What is that in decimal? It's 0.002. All right, remember that. Move over 2 places. So if you have a 0.05% default rate, in decimal that's 0005. Okay, so I need to point that out. All right, so here we go again. We know that there's a $400 return if things go well. The amount that's going to be lost if things don't go well is the whole $10,000. That's gone. Okay. Now, what's the probability that things will not go well? With the 2% default rate, it's 0.02, so that's why it's 0.02 here. What's the probability that everything will be fine? Well, if they don't go bad, they're going to go good. So 1 minus 0.02 is 0.98. So here's a probability that they're going to go well. The 4% is the return, not the probability it's going to go well. Now we can put all this in a table and then find the expected value. Okay, $10,000 investment, 4% return, that's here. Here's my potential loss of $10,000. 2% default rate in decimal, 0.02. Then the probability that it's going to go well is 0.98. The expected value is 400 times 0.98 minus 10,000 times 0.02, and the expected value from this is $192. Now let's see what happens if the default rate goes to 12%. Okay, you've got a 4% return, so you stand to come out $400 to the good. You could lose your whole $10,000. That's there's minus 10,000. If the default rate is 12%, that's 0.12 chance that things are going to go wrong. The chance that everything will go right, or the probability, I'm sorry, that everything will go right is 0.88. We multiply these together and add them, which actually is subtraction here. We find that we've got a loss. The expected value in this case is a loss of $848. This is what you're going to expect to lose. Of course, you're not going to lose exactly that amount. Everything might be fine. You might lose $10,000, but it gives you an idea of what you're looking at to work the problems out this way. And this is called the expected value. Now on the homework, I asked you to find the default rate at which the expected value would be 0. So let me show you how to set that up. Okay. The expected value, let's just use this case, is 400. All right, I'll use this case. Let's let I'll let D be the default value. That's D. What is this? It's 1 minus D. Okay, so the expected value is 400 times 1 minus D minus 10,000 times D. It's another 0 here. And I know that expected value that I want is 0. I want to find out when that's 0. And what default rate can I expect to get nothing back? And after that, it's going to get worse. All right, I just solved this problem. It's algebra. This is 400 minus 400D minus 10,000D equals 0. So I just solve for D. D is, we've got minus 400 divided by negative, and I think that's, all right, I guess I have to use a calculator since I can't remember that off the top of my head. All right, I come up with 0.0384, well, round up to 5. Okay, what is that in percent? 3.85%. Default rate, then the expected value would be 0. Now let's do some insurance problems. Okay, so you have, we'll look from the insurance company side here. Later we'll do the warranty problems. We'll look from both sides. Okay, let's say you have a life insurance policy and it's worth $1 million. All right, and they charge you $300 a month for it, which means we'll do it annually. $3,600 annually goes to the insurance company to insure this person for $1 million. From their standpoint, they either gain $3,600 that year or they have to pay out $1 million. But they do get to keep the $3,600 that they took in, of course. So they have to pay out $996,400. Remember, they keep the payment either way. Right. There's a whole field called actuary sciences, and it's a field that mathematicians can go into, and they work for insurance companies and they work out all of these risks. It's sort of like being a super accountant, but it's sort of beyond that. You have to, know a lot of mathematics, and there's several levels of tests. So if you're interested in mathematics and you want to make a career out of it, you might consider actuary science. So these people employed by the insurance companies work on all these statistics. So they know that the probability that a 30-year-old is going to die in the next year is, and this is in decimal, 0.001014, or about 0.1% chance that a 30-year-old will die in the next year. So what's the probability they're going to live for the next year? It's 1 minus that amount, and we have that right here. From that, we're going to construct a table. So this is the amount they can keep, probability they can keep it. Here's the amount they stand to lose, and the probability of losing it. The expected value, I'll go back to my color scheme here, multiply the two yellows together and combine that with the green numbers, and I find that the expected value is about $2,500. So the insurance company on this policy would expect to keep $2,500 off of that 30-year-old paying $300 a month. That's a little high for a 30-year-old, for $1 million insurance company. All right. If the risk changes, this expected value will change drastically. But instead of doing that problem, let's go and do some extended warranty problems such as are in the homework. Okay. So I'm just going to give a scenario here, and I think you can extend it pretty easily. You don't. We'll do some tables later, but initially we'll start off without tables. Let's say you buy some item, $1,200 TV or something from some company, and let's say that there's a 5% chance that it will break, and I'm not going to worry on it repair costs. Let's just say break means no good. So the 5% chance is going to break in the next 2 years. Right. If I do not buy the warranty that they're trying to sell me, then my expected cost, I'll say EC instead of expected value, expected cost is going to be 1,200 times 0.05, which is $60. So for the next 2 years, I'm kind of looking at a potential of $60 risk. Of course, if it breaks, I have to pay the whole $1,200 to get it replaced, or or nothing happens altogether. But that's the expected value without the warranty. Now they're going to offer me a warranty. It's going to be $50 for the 2 years total. I'll pay $50 to get a 2-year warranty. Okay. Now in this case, what is my expected value here? My expected cost? Okay. Well, I have to pay the $50 for the warranty anyway, so I have to pay that right up front. Then, what is the chance it goes bad? Is 0.05. Chance it's going to go bad, but I won't have any repair costs at all. That's 0. So in that case, my expected value is 50. Doesn't look like much of a savings when you look at it this way, and some of it you buy these just for quote-unquote peace of mind. Okay, let's look at it in one more stage. Let us say that they charge you $50 for this warranty, but if you have to have the TV replaced, they're going to charge you a $100 fee. So you have to pay $100, like a deductible. Okay, what are your expected costs now? $50. And there is a 5% chance you're going to have to pay out that $100. So you work that up. Now it's a $50. About the same as the risk that you're taking by not getting any warranty at all. Okay. Now let's look at it from the standpoint of the people writing the insurance policies. All right. Remember, this is a $1,200 TV. But an insurance company buys in bulk, so their replacement is probably, say, $800. They aren't going to pay, retail cost to replace your TV. Same 5%, and they charge $50. So let's just look at that with no deductible. All right, I'm going to do the tables here. So they stand to keep $50. All right, and what's the probability they're going to keep that $50? It's 0.95. What do they stand to lose? Well, they might have to buy an $800 TV, but they keep the 50, so it's minus 750, and there's a 0.05 chance for that. And somewhere here I've lined. I could put the lines here, but I won't try it because I'll probably just write over them. Okay, so now what is expected value to the insurance company? It's 50 times 0.95 minus 750 times 0.05, and that's something like $10. Okay, so the expected value on every policy is $10, and that's pretty good. You sell 1 million of them, you've got $10 million. Okay, they usually don't have a real high margin on these. Now let's look at what happens and how to do the problem if they charge the $100 deductible. Well, you still can have the $50, and there's a 95% chance the $50 you're going to keep it. Remember to do these probabilities in decimal, not in percent. Right. Now, if they have to replace a TV, they get $100 from you. They get to keep the premium. Okay. So now it's only minus $650 cost to them to replace that TV, and it's a 5% chance they have to do it. For what's the expected value here? It's 50 times 0.95 minus the 650 times 0.05. In this case, I think it comes to like $15. So by charging that $100 deductible, they increase their expected value on the TV.